Hello, this is a lecture on stochastic dynamic programming. Stochastic dynamic programming can be used for operating the reservoir for reservoir operation. So it would derive this optimal operating strategy from Bellman's backward recursive equation. Earlier we were talking about dynamic programming and Markov chain analysis. Essentially, stochastic dynamic programming blends the two. It essentially considers the dynamic programming, which we have discussed earlier. So in dynamic programming, if you remember, it's a multi-stage decision making. So you have different stages and different states. So using backward recursive equation, if you make at a given stage or period, you can say an allocation of xn, this would alter the reservoir state Sn to Sn minus 1. But this decision of allocating xn would give us a revenue of Rn. Now the state has been changed for the coming periods. So in stage n minus 1, if we make this decision of allocating xn minus 1, this would alter the state of the reservoir from Sn minus 1 to Sn minus 2. But this would give us revenue of Rn minus 1. If you just keep on doing for the different stages recursively, then at stage number 1, you have, if you make the decision of allocating x1, this would alter the state from S1 to S0, and this would give us revenue R1. So using an equation, we have tried to illustrate it using this equation. Remember, depending on the context, maximizing or minimizing. Because of the current decision xn, we would obtain revenue of Rn. And in subsequent stages, this would have altered already the state from Sn to Sn minus xn, and the revenues which you can obtain from subsequent stages is Fn minus 1. So this plus the revenue or the benefit or the cost which we have incurred when they are summed, that would give us the current optimal benefit or cost, basically. So this is from dynamic programming. So in stochastic dynamic programming, what has changed, what has been changed is only this, the P superscript J subscript PQ, which is the transition probability matrix, which we have learned in Markov chain analysis, basically. So here, similarly, we are supposed to make the optimal decision on xj. So in making this decision, it would give us the cost or benefit B, and then from uh, uh, suboptimal decisions, accumulated suboptimal decisions over the last n minus 1 stage, Fn minus 1 or j plus 1, where the j is the stage and n is the period. Yeah. So at the j plus 1 stage over the n minus 1 stage and over the j plus 1 periods, so we can obtain, or rather the n minus 1 periods and the j plus 1 stage, then you can obtain the suboptimal benefits or costs. The only thing which has been added this time is the transition probability matrix, the PQ, for every stage of J. Yeah. So this is the stochastic dynamic programming basic equation. We are supposed, for reservoir operation, we are supposed to discretize the storage space. You may remember in Markov chain analysis, we're trying to divide the storage space into different segments. Remember, for example, here, we're talking about, in this example, we were discretizing a storage space of 3 units. For the first 0 to half unit, state 0, half to 1.5, state 1, 1.5 to 2.5, state 2, and 2.5 up to 3, uh, state 3. So obviously, the last state and the first state have got half units, whereas the rest they have got one unit. Yeah, so we're trying to discretize the storage space kind of like this. Now, there are different ways of storage discretizations. Among others, you can talk about the classical scheme or Savarinsky scheme or Moran's scheme. Whereas the classical scheme would divide the storage space in much more number of storage discretization members. The Moran's scheme would divide it into one less than the classical scheme, whereas Savarinsky's scheme would divide the storage space into two less than the classical scheme. Not only the number of storage discretization members, but the way it discretizes is different. Whereas in the Moran's scheme, it would divide it into equal segments. But the classical scheme and Savarinsky's scheme would divide the first storage space into delta S over 2, the last into delta S over 2, all the rest into delta S. So the way it discretizes is also different among the different storage discretization schemes. We are going to, you can have a flow chart for developing your storage stochastic dynamic programming model. So we are going to denote the different states of inflow and storage for different times. So we are going to present at time t the inflow state to be I, so that would give us QIT, and at time t plus 1, inflow state to be J, so that should give us QJT plus 1. Whereas for the storage, at time t, we are going to denote the storage state as K, so SKT. And at time t plus 1, in successive periods, we're going to denote it as L. So you do have SLT plus 1 for the storage state. Now, we are going to represent the release. The release is dependent on the storage state at time t and t plus 1 and inflow at time t. So this equation is basically the equation which is derived from Pontoni's equation, where St plus 1 is equal to St plus Qt minus evaporation minus release. Just rearranging to find the release out of this Pontoni's equation. The only thing which is added here is the states. So the release, the reservoir release is dependent on the storage class intervals K and L and inflow class interval R for period T. So R killed is equal to SKT plus QIT minus EKLT minus SLT plus 1. The evaporation is dependent on the initial and final reservoir states. So it would have EKLT. Since the inflow is random variable, the reservoir storage and release are also random variables. Now we are going to denote the system performance for period T as P killed. So this system performance is dependent on the reservoir state at time T and T plus 1 and the inflow state at time T. So the system performance could be measured in different ways. We are talking about amount of hydropower generated with the release of R killed from the reservoir and the reservoir storage, which determines the head available for power generation at the beginning and end of the periods. If you are talking about irrigation, this could be expressed in terms of deficiencies of the irrigation demands. So using backward recursive equation, we are going to represent the system performance or the whole benefit or causes at different steps. So we can denote each time period a stage in the dynamic programming that goes from n is equal to 1 up to t is equal to capital T. So the stage keeps on progressively increasing from 1 to it just keeps on increasing indefinitely. Whereas the period starts from the end of the period which you are considering, capital T, and then it progressively decreases to 1, and it starts all over again at capital T. So you have the period on one side, which is cyclical, but the stage progressively increasing from 1 to indefinitely increases. Since we are considering backward recursive equation, the period should start from the end of the period and then progressively goes down to 1. Let's say if you are talking about monthly time period, this would mean we start at period 12, essentially on December, and then we talk about November, and then we talk about October, September, using backward recursive equation. And then we go to January. And then we start all over again at December. So the period cyclically goes from 12 to 1, and then it starts from 12 to 1 again. But the stage would progressively increase if you are considering monthly values. If you are considering biannual values, so it starts from 2, 1 to 1, which is essentially summer, winter, summer, winter. It keeps on increasing, cyclically changing. But whereas the stage would progressively increase indefinitely. You can represent using the given system performance equation. You can represent, remember, the initial equation which we were talking about for using Bellman's recursive equation. Yeah. So the benefit or the cost because of the decision, because of successive decisions at the jazz stage or the end period is denoted like this. This is basically the same as when you are talking about, let's say, for period or for stage 1, basically, yeah, and period capital T, there is no successive stage, essentially, yeah, there is no successive stage. As you might remember from the dynamic programming earlier, here you can see right from stage 1, there is no stage, preceding stage, yeah? There is only successive stage, yeah. Or you can say, you can see from here, for example, being in stage number 2, the preceding stage would be stage number 1. Being in stage number 1, I'm talking about the end now. Being in stage number 1, there is no preceding stage. So in the equation, in that set of equations, yeah. So the summation term would be, by the summation term, I'm talking about in this set of equations. So the summation term after the b sj plus 1i, the summation term would be 0 because there is no successive stage after stage 1. So when you talk about for stage number 1 and period, the last period, there is nothing to be summed, but it's just be killed only. And then we are going to maximize that. But when you want to do it for stage number 2 and the next period, which is t minus 1, there is something to be added. Yeah, something to be added, obviously. So the general equation for the n's stage and the t's period would be kind of like this. So this is a general relationship. So ftn, t is the period, n is the stage, is dependent on the storage state at time t and inflow state at time t. This maximization, it could be contextually minimization if you are talking about cost days. But if you are talking about benefits, then maximization. Then be killed. That is the benefit which you can obtain because of the decision to allocate xj currently. Yeah, so be killed. That's the system performance. The system performance is dependent on the storage state at time t, storage state at time t plus 1, and inflow state at time t. Be killed hence. Plus summation of Pij. Pij is the inflow transition probability matrix. So for the inflow to change from state I to state j at period t times the summation of the transition probability matrix times suboptimal cost or benefit at period t plus 1, next period, and at stage n minus 1, the preceding stage. So this is also dependent on the storage state at time t plus 1 and inflow state at time t plus 1, which is j. We're going to check this optimal cost or benefit for only the feasible case of L. If it's going to be negative, then that's not feasible in any negative release. So this is a general equation which we frequently use. Now, without further detail, let's go to an example. Here is the problem. We are going to use stochastic dynamic programming for reservoir operation. You could have used stochastic dynamic programming for water allocation, since we have used dynamic programming already for water allocation. This time around, stochastic dynamic programming, we are going to use it for reservoir operation. So the question is, obtain a steady state policy for the following data when the objective is to minimize expected value of the sum of square deviations of the release and storage from their respective targets. That's the objective, which we wanted to minimize, remember? Over a year period with two periods. We've got only two periods here, period 1, period 2, winter, summer. Neglect evaporation loss. If the release is greater than the release target, then the deviation is set to 0. Only when you have got deficiencies, we want to minimize. So if the release is greater than what is expected, then we don't have any deficit. So we set the deficiency to be 0. The target storage is given as 13. Target release is given as 13. So the system performance is expressed kind of P killed is equal to the release minus the target release square plus the storage minus the target storage square. So this square deviation from the target release and target storage we want to minimize. Inflows and storage for period 1 and for period 2 they are provided here. Inflow transition property matrix from period 1 to period 2. In period 1 being instead of 1, in period 2 being instead of 1 or 2, in period 1 being instead of 2, in period 2 being instead of 1 or 2 is provided, or in period 2 being instead of 1, and in period 1 being instead of 1 or 2, or in period 2 being instead of 2, and in period 1 being instead of 1 or 2 is provided here. So you do have the inflow transition probability matrix for the two periods are provided. Now, we want to compute the system performance using the equations given. Target storage is 30, target release is 30, remember. Now, we know the system performance is dependent on KIL. K is the storage state at time t, I is the inflow state at time t, L is the storage state at time t plus 1. So we are going to compute B killed. But before we compute B killed, we need to get R killed. Yeah. R killed is already given here. R killed. So you need to have SKT, you need to have QIT, you need, well, evaporation is 0 actually, so that term is 0, SLT plus 1. So having these values, then you can obtain the release at time t. Yeah. Now, since the system performance is dependent on KIL, and K can assume only two values, either 1 or 2. Storage state can have only two values here, 1 or 2. The inflow can have only two values, 1 or 2, as you can see. So the states, the inflow states and storage states are just two. Yeah. So K can have only two values. I can have only two values. L, which is the storage state in the next period, can have only two values. So from permutation, one can understand that for different combinations of K, I, L, which each one of them can assume only two values, the possible states combinations for a single period is going to be 2 times 2 times 2, which is 8. So you are going to have 8 combinations for each period. So in period 1, you may have here K could assume 1, I could assume 1, L can assume 1, or 1, 1, 2, or 1, 2, 1, or 1, 2, 2, or 2, 1, 1, 2, 1, 2. And talk about the states of K, I, and L. So you have these 8 combinations. The same is true for period 2, different combinations, but the resulting values are not the same actually. Now, let's first discuss on state for period 1. For period 1, I'm talking about for period 1, when K is equal to 1, the value of the storage at time t for period 1, when the storage we say is in state 1, that would mean here for period 1, when the storage is in state 1, it means SKT is 30. So that's going to be 30. Now, in period 1 again, if the inflow is 1, inflow is in state 1, means for period 1, yeah, inflow is in state 1 means 15. Means 15. In the next period, storage is in state 1 means you can see while being in period 1. The next stage means period 2. So in period 2, essentially, an inflow state of, a storage state of 1 means in period 2, storage state of 1 means 20. Yeah, so that's going to be 20 here. So here, we know the values for SKT. We know the values for I. We know the values for L. So using the release formula, remember, using the Archild formula, which is this equation, yeah. So you can use this equation maybe just to, yeah, you can just use this formula if you wish. So maybe I can just put it somewhere here, the equation, so that you can easily refer to what I am talking about. So R killed is equal to SKT plus QIT minus EKLT, then SLT plus 1. Yeah. So you can see here this set of equations. I think that's crystal clear, isn't it? So So you can see here the values of R killed. Yeah. And then SKT, QID. Basically, the value of evaporation is zero. Huh? Evaporation is going to be zero. So to compute R killed from here, so we do have every element here. Yeah. So we do have every element. So you can see for the first row, SKT is 13, QIT is 15, evaporation is 0, SLT plus 1 is 20. So 30 plus 15 is 45, 45 minus 20 is 25. So R killed is actually 25 here. Yes? So we're going to evaluate now the system performance, which is SKT minus TS. Target storage is 30. SKT is 30, so 30 minus 30 is 0. 0 square is 0. R killed is 25. Target release is 30, so 25 minus 30 is negative 5. Negative 5 square is 25. So we are going to sum the two. We're going to sum the two, so which will give us 25 here. Similarly, let's go for this case. When K is 1. K is 1 means for period 1, storage state 1 means 30. Similar with the above. And the inflow state of 1 means 15. But the storage state in the next period of 2 means 30. So storage state in the next period of 2 is essentially 30 from here. So using those values again for the next row, you can find 30 plus 15 is 45, 45 minus 30 is 15. So R killed is 15 here. So SKT minus TS, SKT is 13. Target storage is 30. 30 minus 30 is 30 is 0. 0 square is 0. This one is 15. Then 15 minus 30 is negative 15. Negative 15 square is 225. Then we add the 2. We add the 2. That should give us 225. Now let's move to the other one. The third option. 1, 2, 1. SKT is 13. Inflow state in period 2 of 2 means 25. Inflow state in period, in period 1. Inflow state of 2 in period 1 means 25. So in period 1, inflow state of 2 means 25 for period 1. So using those values for the third row, so 30 plus 25 is 55. 55 minus 20 is 35. So R killed is 35. Since SKT is 30 again, 30 minus 30 is 0, 0 square is 0. But R killed is 35. And target storage is 30. It's more than the what we are releasing is more than the target release. So we don't have deficiency. When target release exceeds, when the release exceeds the target release, then we have to set the deficiency to be 0. Remember here, if the release is greater than the release target, the deviation is set to 0, right? So since it is 35 here, so we are going to put here the deviation to be 0 here. So this deviation plus this deviation is going to be 0 again. So similarly, we just compute. For period 1, you have all the different options 1, 1, 1, 1, 1, 2, 1, 2, 1, 1, 2, 2. It's so continuous. So for period 2, a storage state of 1 means in period 2, storage state of 1 means This is for period 2, storage state of 1, which is 20, yeah, and inflow state of 1, which is 35, yeah. So 1, 1, 20, 35. That's for period 2. 20 here for the storage, 35 here for the inflow. The storage in the next period, while in period 2, next period means period 1, 2, 1, 2, 1. Winter, summer, winter, summer. Yeah, remember when we are representing the times here, we said 2, 1, 2, 1. Okay, so while being in period 2, the next stage means period 1 basically. So in the next period, an inflow state of 1 means while being in period 1 currently, the next period, an inflow state of 1, and sorry, storage state of 1 means that's basically 30. So using that 30 here, using that equation for article, 20 plus 35, 20 plus 35 is 55. 55 minus 30 is 25. So article is 25. Now SKT minus TS is going to be, SKT is 20 here, minus target storage is 30. So 20 minus 30 is negative 10. Negative 10 square is 100. Since article is 25 here, 25 minus target storage of 30 is negative 5. Negative 5 square is 25. So when you sum the two rows, which is 100 here and 25 here, that should give you 125. So this way we just complete the table for period 1 and for period 2, values for B killed. Only values for B killed we have so far obtained. Yeah, only the values of B killed. Now we have to sum the product of the transition property matrix and the suboptimal benefit or costs in the subsequent steps. Yeah. Now we start, once we have said this, we start for period 1. So essentially, what we are doing is we are going to obtain for period 1, sorry, for stage 1, and period 2. We start with that one first. Yes? So first for n is equal to 1 and t is equal to 2. We're going to compute that. Essentially, let me just put kind of a bracket. That would be, I think, better, I guess. So it's going to be like, now fill, and maybe color is better, I guess. Maybe red. Yes. And then line style, it is allowed. So let me just make it like 4 is okay, I guess. So we talk about for this part, t is equal to 2 and n is equal to 1. So first for this part, t is equal to 2 and n is equal to 1. There is no successive stage there. So obviously the formula is going to be minimizing B killed only. Mind you, here the system performance, we want to minimize, not maximize, because that's the deficiency between target storage and target release. Huh? So for the first, for t is equal to 2 and n is equal to 1, we're going to compare, we are going to compute. Next period is going to be n is equal to 2, so period is equal to 1, and stage is equal to 2. The stage is progressively going to increase, whereas the period 2, 1, 2, 1. Remember from here, 2, 1, 2, 1. So first we have just computed here. Next we'll continue with the next one, which is actually for stage 2, and period 1. So n is equal to 1 first, n is equal to 2, and then n is equal to 3. It's all continuous, huh? So here we start with sorry, n is equal to 1 we start, and then progressively n is equal to 2, and then n is equal to 3. It's all continuous, yeah? So first, for n is equal to 1 and t is equal to 2, so this minimizing peak yield. For t is equal to 1 for the second stage and period 1 is going to be this formula now. Maybe maximize that. Yeah. So for the first one, we are going to do this formula for possible values of storage state and possible values of inflow state. So F21 Ki, we are going to find the minimum of this peak yield. For possible feasible values of L can have value of 1 or 2. When L is 1, so we are talking about K is equal to 1, I is equal to 1, yeah, K is equal to 1, I is equal to 1, and when L is equal to 1, which is 1, 1, 1, the system performance, that's for period 2, system performance for period 2, 1, 1, 1, from the previous table for period 2, that's for period 2, 1, 1, 1 is going to be 125. Yeah, so that is 125 here. When L is equal to 1, but when L is equal to 2, when L is equal to 2, that is 1, 1, 2 for period 2 still, mind you, T is 2. So at K is equal to 1, I is equal to 1, and L is equal to 2 for period 2, 1, 1, 2. It's this row, 1, 1, 2. It's 325. So the system performance is 325. We are looking for the smaller of the two. For the smaller of these two, which is 125. And this 125 is obtained when the storage state is instead of 1. Yeah. The next possibility is K could be 1 or I could be 2, where L could have either 1 or 2. When L is 1, yeah, for different feasible values of L, we are going to compute that. When L is 1, this would mean 1, 2, and L is 1 for period of 2, that is 1 to 1 for period of 2, 1 to 1 for period of 2 is 100. Yeah, it's 100. And then 1 to 2 for period of 2 is 125. Yeah, and the smallest of the two, is 100, and this has occurred when L is 1. Yeah. Similarly, 2, 1. 2, 1, and for feasible values of L could be 1 or 2. When it is 1, it's going to be 0. 2, 1, 1. For period 2, 2, 1, 1 means 0. 2, 1, 2 means 25. And the smallest of the two is 0. That would occur when L is 1. 2, 2, 1, which is 0. 2, 2, 2 is 0. The smallest of the two is 0. That could occur either when L is 1 or L is 2. Now, we have just finished for period 2 and stage 1. Next, we're going to do for next stage, which is stage number 2 and period 1. Yeah? So, that's going to be for n is equal to 2 and t is equal to 1. Yeah? using the general formula again, this would mean minimizing B killed. In the B killed formula, the T is 1, obviously, and then summation of Pij, and then the superscript is T, yeah. So here we are writing F, here we are writing F1 to Ki, minimizing B killed, the T is 1 here, here T is 1 here, N is 2. Remember in the general equation here, so here T is 1, stage is 2, here T is 1 here. This is not maximization in this case, minimization in our case, because we are talking about the depth sheet. So Pij, here there is T is 1 here. And then the N minus 1, N is obviously 2, so N minus 1 is 1. And T was 1 here, T plus 1 is going to be, the next period is going to be 2. So this is 2, and this is N minus 1 is 1. Yeah, for different values of L and J, we are going to compute that. And this is the transition probability matrix. Yeah. So here we can find F12 for different possible values of K and I. Let's assume K is going to be 1, I is going to be 1. For different feasible values of L could be 1 or 2. When L is 1, this would mean B kill 1, which is when K is 1, I is 1, L is 1, period 1. So the B killed value for period 1 for 1, 1, 1 is going to be from here. For 1, 1, 1 for period 1, we just read from this table, which is 25. So that is 25 already. So the first term is 25 here, plus summation of the transition probability matrix. Yeah. P, I is 1, we have said already. For different possible values of J, so J could be 1 time, the other time is going to be 2. That is the inflow state in period T plus 1. It could either be 1 or 2. When it is 1, then we are talking about transition probability matrix from 1 to 1. For period 1, transition probability matrix from 1 to 1 means, for period 1, transition probability matrix from 1 to 1, inflow state of 1. This is for period 1, right? Inflow state of 1 to 1, it means 0.5. So we use 0.5 here. And then F1 to Lj, value of L here is 1, yes, and the value of J currently is 1. So F21, 1, 1 from the previous table, the table above, you can see F21, you can read from this table here. So F21 values, you can read it in this column actually. The value of F21, you can read from this column. So for the first case, when the value of L is 1 and J is 1 means F21, 1, 1 means 125. So using 125 here plus. And then when J is 2, then we talk about inflow transition probability matrix from 1 to 2 for period 1. For period 1, transition probability matrix from 1 to 2 is 0.5 here. So we use 0.5. Yeah. And then the value of F21 Lj is going to be F21 when L is 1 and J is 2, 1, 2, which is along this row. You can obviously see that is 100 here. 100. So that should give you 137.5. So that's the case when L is 1. Yeah, when L is 1. You can talk about the case. Yeah, that's the case for when L is 1, 137.5. When L is 2, that would mean be killed for period 1. It's 1, 1, 2 for period 1. 1, 1, 2 for period 1 is obviously 225. So we use 225 here plus transition property matrix from state of 1 to 1 is 0.5, which we know earlier. And from F21, value of L is 2, value of J is 1. That is basically 2, 1 is this row. So that is 0 here. Yeah. And then the transition property matrix from a state of 1 to 2 is 0.5. And then F21, when the value of L is 2 and the value of J is 2 is this row actually. Yeah, the last row. So you do have this value here, 0. So that should give us 225. The smaller of the two is 137.5, and this 137.5 has occurred when L is 1 actually. Yeah, so we just continue similarly. We just finished this table. So we just completed the case for stage 2 and period 1. Once you finish for stage 2 and period 1, we just continue with the next stage, which is the stage 3, but the period is 2 because the period progressively it goes from 2, 1, 2. So T is 2 and then N is 3. Yeah, the period progressively, the stage progressively increases, whereas the period is going to be 2, 1, 2, 1. Yeah? It's a two period problem, right? So we're going to do it. Earlier, we just did it for T is equal to 1 and N is equal to 2. Next, we are going to do it for T is equal to 2 and N 3. Yeah. So similarly, we just finished that. Then we just fill this table. In filling this table, we are going to depend the F12, which is the previous table actually. Values from here, we are going to use. When we compute F3, F23 here, we are going to use the values from here, the immediate predecessor table, these values here. And then we finish. And then we just go to the next one. The stage progressively increases. Earlier it was 3, and now it becomes 4. It becomes 4, So, and this stage of 4 and period is 1. 2, 1, 2, 1, Stage next is 5 and period is 2. Yeah. So when we try to find out this one, we have to rely on F23 here. When we want to find out F25, period 2 and stage 5, then we have to use stage 4, period 1 from here. Yeah, so that way we just complete, keep on working. Yeah, then we would say we have obtained a steady state solution because the problem is to obtain a steady state policy here. Steady state policy. We can claim a steady state policy is achieved when the result from successive similar periods are the same, which is, for example, in stage number 8, which is for period 1, and stage number 6, which is for period 1, the corresponding results are kind of this much amount. Here, it's this much amount. So if you just deduct from successive similar periods, winter, winter, or summer, summer, then the difference is almost the same. So you can see here, the difference is almost the same for period 1, stage number 6, and stage number 8. Or you can talk about period 2, stage number 7, and stage number 5, It's almost the same. Now we can say we have obtained steady state. So the final outcome is the outcome which we have achieved for each of the respective periods. So this is going to be the steady state policy for period one. Yeah, steady state policy for period one here. And this is the steady state policy for period two, which you have obtained from stage seven. In stage seven, we have already achieved this result. So this is going to be for period two, basically. So what does this mean? This means in period one, let's say that's winter period, if the storage state is in one, and if the inflow state is in one, then the storage in the next period shall be maintained in state one. If the storage state is if the storage state is, let's say, in a 1, if the inflow state is in state 2, then the storage in the next state should be maintained at 2, it means. Similarly, k of 2 and k of I of 1, then in the next period, the storage should be maintained at 2. If it is 2 and inflow of 2, then the storage in the next period should be maintained at 2. But for period 2, irrespective of the inflow state and the storage state, we have to maintain in the next period storage state of just one, it means. So this is how we can do the reservoir operation using the stochastic dynamic programming. Now we have just completed the section on stochastic dynamic programming. Then we talk about river basin modeling. Models are basically abstractions of reality. They take the same type of inputs almost like the natural process, and then they try to mimic the natural process. You may have analog models, you can have physical models, or numerical or mathematical models. Physical models are basically structures, right, with a certain scale that you construct in the laboratory. Analog models is just like you can just have a relationship between Ohm's law, which says resistance equal to voltage over current, to Darcy's law, where Q is equal to negative K permeability times hydraulic gradient times cross-sectional area. Yeah, so some way of representing the water resource systems using electrical systems, yeah, as analog models. But here we talk about mathematical models. By a set of mathematical representation, hydrological models are basically mathematical models. You can represent models on the base of process or spatial scale or temporal scale or solution set, how the solution is being obtained. On the basis of process, you can have physically based model, which sometimes we call it white uh, box models. In case of physically based or white box models, processes are represented in detail. Whereas in black box models or empirical models, it's just very coarse. There is no clear representation of cause and effect representation in the catchment. Whereas conceptual models or gray box models is somewhere in between. Yeah. If you just look at Mike Shee, for example, is a physically based model. Black box, for example, artificial neural network, it's a black box model or system theoretic model. Conceptual model, for example, Nash model. It's conceptual model from your studies in applied hydrology, Nash model. So you do have on the basis of process, you can represent in very much detail, like in physically based or white box models, on very coarse, like in black box or system theoretic models, or somewhere in between in conceptual models. You may also classify models on the basis of the spatial scale, lumped or distributed. When the whole process is averaged at catchment scale, then we call it lumped model. Whereas in distributed model, you may represent process at sub-catchment scale, a little bit distributed, or you may have in a very fine disaggregation scale, like on grid scale, or somewhere in between at HRU, hydrologic response unit. For example, ArcSWAT is distributed on the base of hydrologic response unit. Whereas MICSHE, it works on the base of grid scale. HMS on the base of subcatchment scale. You may also represent on the base of temporal scale. Some would represent events, like very commonly used in HMS. Of course, you can use HMS for continuous representation. Or you may use ArcSWOT, which is very much used for continuous time representation. On the base of solution method of solution, you may also represent numerically or using analytically. Of course, analytically, if it's not very much simple type of model, it's difficult to find solution using analytically. But numerically, using finite difference or finite element or boundary element or any other numerical techniques could be employed. That's a very common type of method of solution in many models currently. So there are different ways of representing models. Details of the lecture note is annexed in this lecture material. So with that, we have finished the whole section course material for this course. I thank you very much.